Welcome back to another algebraic graph theory seminar. This week we have our very own Chris Godsil telling us about the matching polynomial.
Thanks, Max. Thanks, guys. Okay, so I'm going to talk about the matching polynomial. I'm going to be talking about some of the properties that make it interesting and then discussing a couple of open problems that I've been thinking about just the last week or two. So, well, first thing is I've got to give you a definition. So the matching polynomial, I view it as a generating function for the number of k matchings in the graph. So a k matching is a collection of k edges, no two with a vertex in common. And so for any graph X, we've got a sequence PG0, which is 1, PG1, which is the number of 1 matchings, which is generally called the number of edges, and then PGK, the number of k matchings. And so when you want to deal with sequences, it's best to stuff them into a generating function. And this generating function is a little twisted. Instead of just being sum of px comma k t to the k, we've got a sign factor of minus 1 to the k, and we're using t to the n minus 2k rather than t to the k. Now, so someone told me once, you're looking for the generating function for the sets not covered by matching, but let's not worry about that. Okay, so just to get started a bit, just pick a couple of graphs and just get someone to know what's going on. So we want to get the matching polynomial for this graph, the first graph here, then, well, okay, we can write down a bit. We know that it's a degree 5, so it's going to be t to the 5th, and there are 5 edges, so we're going to get a 5 times t cubed. Now, we only get either all odd terms or all even terms because we've got that n minus 2k there. So, and so the next term is just some constant times t, the number of 2 matchings. Now, if the number of 2 matchings, when you pick an edge, now how many 2 matchings contain that edge? Well, if you throw away 2 and 3, the graph left over has got 2 edges, so you'll get 2 1 matchings containing that edge. And a similar calculation shows you get 2 on that edge. And if you delete those 2 edges, the graph left over is a star and doesn't have a, so that there's no way of finding a 2 matching in there. So you get the answer plus 4t. Okay, so that gives you a bit of an idea how the matching polynomial works, some of the factors, properties. My 2 graphs there, I'll leave the second one as an exercise. As it turns out, it has the same matching polynomial. So they're not entirely random. Well, it happens sometimes, and we're talking more about that towards the end of the talk. Now, once you start thinking about that, I just ran through some of the smaller examples on the right there. So they're some examples of co-matching graphs on 4 and 5 vertices. The somewhat crazy thing is the first and third of those graphs consist of a graph and its complement. And I don't really understand that, but it seems to be happening quite a bit. But anyway, so that's the matching polynomial. You saw a way of sort of computing the coefficients. Now, the problem is that getting the number of matchings in a graph is NP hard. So, but the recursions work well for small graphs. Now, we can be a bit more sophisticated and write down a couple of recurrences. And the first one involves edge deletion. So we're going to have a graph, and we're going to pick an edge in it. Now, there's 2 sorts of k-matchings. There's the ones that you don't use the edge E and the ones that do. Now, if you don't use the edge E, you're a k-matching in X drop E. And so that's counted by the first term there. Okay. If you do use the edge E, then you throw away that edge and the 2 vertices are joined, and you get a graph X with 2 vertices deleted, and you're staring at a k minus 1 matching that graph. And because there's a sign factor in there, you get a difference rather than a sum. So that's the edge recursion. Okay. Now, it's nice and quite convenient. And just to complicate things a bit, I decided to write down the corresponding recursion for the characteristic polynomial. Okay, and the first 2 terms are the same, but there's this rather weird 2 square root term in the end there. I won't be explaining that today, but it's a product of, well, involves X drop A, X drop B, the graph X drop B you started with, and X with A and B deleted. Now you can show, and that's scroll at the bottom, that square root term will vanish if the edge is a cut edge. And that's easy. Okay, so that if your edge is a cut edge, then the edge recursion is the same in both cases. But the point still is that for the characteristic polynomial, you've got that second factor. Some sense it probably goes back to one of the theoretical chemist course, and some form of this. Tut also made use of this fact in his proof that graphs with irreducible characteristic polynomial are reconstructible. We won't be discussing that today. Now, there's a second recurrence. We can delete vertices. Now, in this case, we pick a graph. Might as well, I pick a vertex. I'm using 8. Now let's look at the K-matchings. Again, there are K-matchings that contain the vertex A and K-matchings that don't. Now the K-matchings that don't contain the vertex A are easy to deal with. They're just matchings, K-matchings in X with A deleted. What about the K-matchings that do contain A? Well, we can partition them into classes according to the neighbor of A that they use. Okay, so we can break up the set of things we're trying to count into the K-matchings that use A and B, the K-matchings that use A in the next vertex, and so we're going to get a sum, and the sum just turns out to be the sum of the polynomials mu of X drop AB, comma T. So we get a nice recurrence. Now, have a bit of fun with this. If you apply it to the path on n plus 1 vertices, well, when you delete a vertex from the, well, first we start from the left-hand end. That vertex has got exactly one neighbor. So when you delete that vertex, you get a path of length n. And when you delete that vertex and it's one neighbor, you get a path of length n minus 1. And so you get a recurrence. Okay. And that's a recurrence which is satisfied by the Chebyshev polynomials. And so it turns out that the matching polynomial for the path is, modulus and scaling, one of the two families of Chebyshev polynomials. Okay. The matching polynomials of the cycles could be the other family, but we won't be going there. Another interesting case is the complete graph, because in that case, you delete, if you've got a complete graph on n plus 1 vertices and you delete a vertex, then you've got complete graph Kn, and if you delete a vertex's neighbor, you've got complete graph Kn minus 1, and so you get a recurrence that the matching polynomial of Kn plus 1 is T times the matching polynomial of Kn minus n times the matching polynomial of Kn minus 1. This is another 3-term recurrence. So in this case, what you're getting are the Hermite polynomials. Okay. You can also get, which will help you very much, I guess, but you can also get the Laguerre polynomials by working with the complete bipartite graphs. That was observed by Goodman. Another little fact I'm going to use a couple of points is the derivative of the matching polynomial is the sum of the matching polynomials of the vertex leader subgraphs. Now, the same identity is true for the characteristic polynomial. And in fact, it's rather difficult to come up with a definition of some matching polynomial counting structures and graphs, which doesn't satisfy this property. You have to work a bit. So I'm not going to go into details, but the derivative of the matching polynomial is the sum of the vertex leader matching polynomials of vertex subgraphs. And it's not too hard to prove once it occurs to you that it might be true. I want to put one more recurrence, which I'm going to need. So I'm dealing with the one sum of two graphs, X and Y. So I've got a graph with two induced subgraphs, X and Y, having just the vertex A in common. And I've written down two formulas there. They're a bit of a mess, but one's for the matching polynomial and the other's for characteristic polynomial. Now, the important thing is the right-hand side depends on it's determined by 4 graphs, X, Y, and X drop A, and Y drop A. So if you know the matching polynomials of those 4 graphs, you can write down the matching polynomial of the one sum. And similarly, if you know the characteristic polynomials of those 4 graphs, you can write down the characteristic polynomial of the one sum. The identity for the characteristic polynomial is due to Schwenk. And there's a couple of proofs. One is to use determinants, which doesn't help you much when it comes to the matching polynomial. And the other is to use a warp generating function argument. I'm not going to go into that. I just wanted, the point is that since they have the same 2 recurrences here, one consequence of this by a simple induction proof is that the matching polynomial of a forest is equal to the characteristic polynomial. Okay, now the converse is also true, that if the two polynomials are equal, the graph is a forest. But the point I'm making now is that if the graph is a forest, this matching polynomial and this correct polynomial are equal. And that's why those fudge factors -1 to the k and t to the n minus 2k are in there, because the chemists wanted that to be true, for example. I should say the matching polynomial arose in 3 different places, and strictly speaking, it didn't arise first in combinatorics. So there was a paper by Harman and Lieb called on theory of monomer-dimer systems, which worked with the matching polynomial extensively and worked out many of the basic results. Okay. The chemists also used the matching polynomial. I won't go into the explanation of that, but these are chemists working with approximations in molecular orbital theory, and so they were interested in eigenvalues of graphs and things, and they eventually decided they were interested in matching polynomial Z-zeros, and so there's a chemical literature. And the first combinatorial literature is in Riordan's work on Rook polynomials, which can be viewed as just matching polynomials for bipolar graphs. So it's arisen in several different places, which is a sign that might be interesting. Now, so next thing, well, the matching polynomial has some unexpected properties. I mean, the ones I've talked about up to now, these are straightforward recurrences. You count matchings that contain a vertex and don't contain a vertex and split things up. And so we get a bunch of recurrences in a fairly easy fashion. The next thing involves something quite unexpected. Well, there's a relation between the matching polynomial graph and its complement. Well, I just decided the simplest way to do it is just to give you the formula. So if I want the number of perfect matchings in the complement of X, I compute the average of the matching polynomial of X relative to the normal distribution. So 1/2 pi, integral from minus infinity, e to minus 2 squared on 2 times mu. That integral is equal to the number of perfect matchings in the complement. Now, the way I came on this was back in prehistoric times. I was teaching a course actually doing with Brendan McKay in linear algebra, and the students have been set up some examples involving some funny inner products, and so in particular they were given this. You can use the normal distribution to define inner product. You just take the integral of the product of 2 polynomials. There's your inner product. And so if you're going to do any calculations that, you need to know the moments. And so the key thing you need for this is that the number of perfect matchings is equal to the product of the odd numbers less than n. So the point was, in this exercise, they were asked to prove that when, so if you take the empty graph, you're going to get non-perfect matchings in the complete graph. So you're going to have t to the n. So you're asking what are the moments of the normal distribution. And so you have to do this calculation, and well, I say it's just integration by parts, and not even especially difficult. It's a long while since I've done integration by parts, so I don't do it again. But so the number of perfect matchings in the complete bipolar graph Kn is equal to the moments of the normal probability distribution. Okay, and so now to prove the statement above that, it's basically induction on the number of edges, and use the edge deletion recurrence. And the difficult case it is actually the first one, as far as I'm concerned. I mean, the work you go through to get the second. So once it occurs to you, this might be true, and once you know this fact about the normal distribution, then you very quickly get this identity. Now, it's got some interesting consequences. What if I look at the integral for the product of the matching polynomial of Km and the matching polynomial of Kn? Now, these are Hermite polynomials, and this is a product that analysts would care about. And so when you do that integral, well, I don't need to do any integration anymore. I know its number of perfect matchings in the complement of the disjoint union of Km and Kn. Now, the complement of that disjoint union is just the complete bipolar graph Kmn. And if m is equal to n, it has n factorial perfect matchings, and if m is not equal to n, it has none. So what you've established is that integral is 0 if m is not equal to n, and it's n factorial when m is equal to n. And so you've proved that the Hermite polynomials are orthogonal with respect to the normal probability distribution. Okay, And you can do something similar for the Laguerre polynomials if you set things up. I don't know a nice way of using integrals for the Chebyshev polynomials, but you get this quite surprising fact. I mean, it's not immediately obvious if someone just defines the Hermite polynomials in the usual way. It's not obvious that this integral is non-negative. But the counting argument is good. Now, one consequence of this result is that the matching polynomial of a graph determines the matching polynomial as a complement. Now, this is a little surprising because this is false for character polynomial. Okay. Now, to see this, what we do is instead of integrating just the matching polynomial of x, we look at the product of the matching polynomial of x with the matching polynomial of the complete graph on n minus 2k vertices. And so that integral is going to be equal to the number of perfect matching, the complement of that. So that's going to take n minus 2k isolated vertices, join into everything in x, and then count the perfect matchings in that. And you work for a little bit, and you get a constant times number of perfect matchings in the complement of x. Okay. Now, so are there any questions at this point? Okay. So that's certainly one of the more surprising properties of the matching polynomial. And so now I want to talk about an interesting structure related to matching polynomials, which lets us derive a lot of the properties. This can be viewed as a nicely packaged form of the vertex recurrence that I was using earlier. Okay. So given a graph and a vertex in the graph, I'm going to construct the path tree relative to that vertex. Now, what are the vertices? The vertices are going to be the paths in my graph that start with vertex A. Now, these are paths, not walks. They don't overlap. Okay, they start at A. The edges, two paths will be adjacent if one is a maximal subpath of the other. And so here I've worked out an example with one of my first two graphs. So I was taking the vertex 1. And so there's one path length 1. There are two paths of length 2, 1, 2, and 1, 4. And you can see if I go 1, 2, 3, 4, 5, I'm going to get a path length 5 there. And so I get bar. Now, just to amuse myself, we could do the same thing for the second graph. We have 1, and we still get 2, 3, 4, 5. And we can go to 1, 3, and 2, or 1, 3. That should be 1, 3. You get the idea. That's a pretty bad 5. Well, this doesn't prove much. It does tell you that you can get the same path tree from different graphs, which is not immediately obvious. So these two trees are isomorphic. So, okay, so there's the path tree. And it's straightforward to write down. It's easy to write programs to compute it. And the first thing is obviously it's going to be bloody big in general. Okay, but what does it tell us? Well, the theorem is that if I look at the matching polynomial of x with a deleted divided by the matching polynomial of x, that's equal to the character polynomial of t with a deleted divided by the character polynomial of t. Well, it doesn't matter on the right whether you put the matching polynomial or the character polynomial, the trees, they're equal. Okay, and the other thing you get as an easy consequence of this, the proof, is that if x is connected, its matching polynomial actually divides the character polynomial of t. Now, this is quite powerful because this now means you can take spectral results about trees and use it to reduce results about the matching polynomial. And the first thing you can see from this is that the zeros of the matching polynomial must be real because they're equal to the zeros of the character polynomial of some tree. So you get the matching polynomials are real. The next thing is you have a tree with maximum degree delta, then you can show that all its eigenvalues lie in the open interval from -2 root delta minus 1 to 2 root delta minus 1. Okay, and so that gives you the same bound on the zeros of the matching polynomial, so they're real right along that interval. You can, since the largest eigenvalue of a tree is simple, that's the spectral radius, you can deduce that the largest eigenvalue of the matching polynomial, the graph, is simple if the graph's connected. And you can, since you know that the zeros of a graph with a vertex lead that interlace the zeros, so the eigenvalues of a graph with a vertex lead that interlace the eigenvalues of the graph, you actually also get that the matching zeros of x drop A interlace the matching zeros of x. So you're getting a lot of spectral information from one identity. Now, you can generalize there's really more, as a corollary stated here, I can replace, instead of just deleting a vertex A, I can delete any path starting at A. And so then I get matching polynomial of x drop P over the matching polynomial of x is equal to the matching polynomial of T drop P over the matching polynomial of T. Now, it's not trivial, but there's a theorem that tells you that if you delete a path in a tree, the multiplicity of the eigenvalues don't drop by more than 1. So in other words, the rational function on the right here has only simple poles. Okay, so that implies that the rational function on the left has only simple poles. Okay, so now let's be greedy and take P to be a Hamilton path. Then x drop P is the empty graph, and so mu of that is just 1. And so you get 1 over the matching polynomial is a rational function with only simple poles. And so you've proved that if the graph has a Hamilton path, all its zeros of the matching polynomial are simple. Okay. Now I'll be saying more about this shortly, but so one class of graphs, if a graph's vertex transitive, it has a Hamilton path. That's not a theorem, but it's a conjecture, and I don't think anybody doubts it. So that consequence of that would be that the zeros of the matching polynomial of the vertex transitive graph are always simple. Now this is surprising because the zeros of the eigenvalues of a vertex transitive graph, if your graph is not K1 or K2, the eigenvalues are not simple. You can show that a transitive graph has at most n on 2 simple eigenvalues. So this is a situation where the matching polynomial and the characteristic polynomial are differing quite a bit. So the characteristic polynomial for transitive graphs or highly regular graphs tends to have few eigenvalues, but the matching polynomial of a graph tends to have its eigenvalues simple. Okay, now I'm talking about matching zeros and graph eigenvalues. In a certain sense, the obvious and most important zero of the matching polynomial would be zero itself, because the multiplicity of zeros of 0 in the matching polynomial is the number of vertices missed by a maximum matching. Okay, and so the question in some sense, is there any relation between or analogically between the matching theory of graphs and the matching polynomial? And so I'll start with the graph theory. The result I'm concerned with here is Godsil's lemma. And it says you have a connected graph and each vertex is missed by some maximum matching. Then each maximum matching misses exactly one vertex. Okay, so now this looks a little technical, but it's in some sense at the heart of a lot of matching theory, and it plays an important role in the Godsil structure theorem. So it's a simple enough result. Now we can restate this in terms of the matching polynomial. So assume that x is connected. If the multiplicity of 0 in x drop A is less than the multiplicity of 0 in x for each vertex A, then the multiplicity of 0 in x is 1. So this is just a translation of Godsil's lemma into a statement about multiplicities of matching zeros. Okay. Now when you see that, you start wondering, what about other zeros? And well, it's a long story, but the end result is a paper by Ku and Chen. So assume the graph is connected and let theta be a real number if the multiplicity of theta in x drop A is less than the multiplicity of theta in x for each vertex A, then the multiplicity of theta in x is 1. Okay, so that's the exact analog or generalization of Godsil's theorem. Ku and Chen actually give a version of the Godsil structure theorem, but I didn't want to be explaining that today. So I'm leaving that out, but they have the full Godsil structure theorem. Now, this is one reason I was interested in Godsil's lemma in this context is, well, first thing is if you if you have a graph X and a matching 0 theta with multiplicity greater than 1, then there's always a vertex A in the graph such that the multiplicity of X drop A, theta in X drop A is less than its multiplicity in X. You can always bring it down. Now, the proof is simply that if the multiplicity of X drop A is at least as large multiplicity in X for each eigenvalue, each vertex A, then since the sum of the matching polynomials at the vertex isographs is the derivative of the matching polynomial, you deduce that the multiplicity of theta in the derivative of the matching polynomial is at least as large as the multiplicity in the polynomial itself. And that doesn't work. So the fact that the derivative of the matching polynomial is the sum of the matching polynomials of vertex isographs implies that if you have an eigenvalue theta, a matching 0 theta, then there's always a vertex you can delete and reduce the multiplicity of theta. Okay. And so a consequence of this simple observation and the theorem of Q and Chen is that X is vertex transitive and connected. Well, if X is vertex transitive, you know there's a vertex you can delete and reduce the multiplicity of theta, but since it's vertex transitive, all vertices work. And so therefore, by the Q and Chen extension to Godsil's lemma, you deduce that the zeros of a connected vertex transitive graph are simple. Okay. And so, now, as I said, Q and Chen have worked out the full structure theory for the Godsil-Edmonds theorem, and Ku has, I think, in total 5 papers on this topic. So there's a lot of theory there, but I don't think it's really, so he's looked at it, but nobody else has, I think, and it's probably worth some attention. So for the rest of the talk, I want to focus on a couple of problems concerning the matching polynomial. The first one is interesting, kind of cute, kind of fun. I'm not really sure where it goes, but it is interesting. So first one I was thinking about this is that for a lot of people in graph spectra looked at the question about graphs with integer eigenvalues, and in particular trees with all eigenvalues integers. And for a long while, it was an open question whether you could get a tree with all eigenvalues integers and arbitrarily large diameter. And this was eventually settled in a nice paper by Chigvari, but I think that Brouwer got to about 6 or 8 that Chigvari proved that you could get trees of arbitrarily large diameter with only integer eigenvalues. Okay, now results about spectra of trees, it's very often worth asking, well, what can you say, what's the analogous result? For just result can suggest results about zeros of matching polynomials. So the question we're asking here is, which matching polynomials have only integer zeros? And so this question, well, I'm going to state the question posed by Akbari and about 6 people altogether. They ask, are there infinitely many 2-connected graphs with all matching zeros integers? Now, you need to put in some restriction on the connectivity because we can get arbitrarily large trees with all matching zeros integral, so we need to exclude trees. There's a few other classes of graphs we need to exclude, but I'll come back to that. Akbari and his colleagues proved they classified the graphs with these matching zeros were all integers and were simple. And the graphs they found were K1, K2. The 2 graphs I used as my examples on the first slide, and the complement of the disjoint union of C3 and C4. Just as it seemed interesting to me that the matching zeros of that complement are 0, plus or minus 1, plus or minus 2, plus or minus 3. So they're the 5 graphs with eigenvalues simple and with matching zeros simple and integers. They also showed that if you had a connected regular graph with only integer matching zeros, then it was either K2 or the complement of C3 union C4. Now, the thing that's driving this is in the case of the regular graph, you can find reasonably long paths. And now the problem is that long paths force lots of non-simple, lots of eigenvalues and non-integer eigenvalues. Okay, so the point is that if the graph's got valency k, then all the matching zeros lie in interval plus or minus 2 root k minus 1. And there's not room for a long path, so this tends to drive it, but we won't go into that. They also had as nice result, they proved the graph has a perfect matching, and it's not just a union of edges. Has a matching 0 and 0, 1, and so therefore it doesn't have only integer zeros. Now, for reference, it's actually true that if you have a graph and all the eigenvalues are simple integers, you can prove the number of vertices is at most 10. So now, on the other hand, it's comparably easy to construct graphs with simple integer eigenvalues. The first example that comes to mind would be strongly regular graphs or cube-like graphs, k-graphs, Z to D. So you can construct graphs with integer eigenvalues without any problems. And so, with the matching polynomial, as I said, it's not clear what's going to happen. Akbari they said two connected. There's one class of examples that I'll just draw here. I was amusing myself this morning by doing a few computations in Sage and running through all the graphs up to 9 vertices. And this is a graph on 9 vertices with only integer matching zeros. And it's quite easy to prove using the vertex deletion recurrence on the central vertex. So when you delete the central vertex, you've got 4 copies of K2. So the polynomial for that is t squared minus 1 to the 4th. And so you use the vertex recurrence and you discover, yes, for a windmill with 4 spokes like that, or 4 blades, the matching zeros are integers. And the next, so basically you want, or 12 will also work. You want, so the number of blades, you want 2n plus, 2 times the number of blades plus 1 to be a perfect square to get the eigenvalues, to get the zeros to be integers. So this is a connected graph, it's not a tree. Okay. Now, I don't have the patience to run through the 10s, and there's not, maybe there are interesting things happen on 15. Now, the point, of course, is computing the matching polynomial is NP hard. The code in Sage does quite a good job, and you can get matching polynomials for fairly large graphs, but not. It's probably possible to do 10 in Sage. Doing the character polynomials of all graphs on 11 vertices is a major undertaking. Brower and Spence did the computations for 11 and 12 vertices, and Brower told me one of the problems they ran into is they discovered a number of bugs in the Unix file system. So just because there's so many graphs. Okay, so the other question I want to deal with is, well, when co-matching graphs, 2 graphs for the same matching polynomial. Now, my student Kai-Lang Wang worked on some of this for a PhD thesis, so I'll be quoting her in a few points here. So let's start with some background. What about trees? Well, Schwenk, a very remarkable result, proved that the proportion of trees on n vertices that are characterized by their matching polynomial, well, he said characteristic polynomial, but they're the same. The proportion of trees characterized by the matching polynomial goes to 0 as n goes to infinity. Goes to 1. No, it goes to 0. I got that right. So the proportion characterized goes to 0. So most trees have a cospectral mate. Now, I'll say a little bit about the proof. On the bottom part here, I've got 2 graphs consisting of a tree on 9 vertices and another tree attached to one of the vertices in that tree. It's a 1 sum. Okay, so I'm using the same vertex. So it's a 1 sum of a tree attached to either vertex 4 or to vertex 8 in the graph. Now, the interesting thing about that tree on 9 vertices is that the graphs you get by leading the vertex 4 and the vertex 8 have the same characteristic polynomial. Okay. And so if you go think back to the formula I wrote down for the one sum, I said there were 4 graphs involved. X, Y, X delete the joining vertex, Y delete the joining vertex. And so if you think about that for a second, that implies that those 2 graphs have the same characteristic polynomial. Okay, so I was talking with Schwenk once now. I mean, this was done 30 years, and I don't know exactly, it was done a long while ago. And so he didn't have things like Sage around. And I was asking, I asked Alan how he came across this particular tree. And he said he had a stack of cards with a drawing of each tree, up to 9 vertices, I guess. And he was standing in line waiting, queuing up to get tickets for a football game at his university. And calculating while he was waiting, he had to wait overnight or something. These things can be stupid. So he was working one out by hand. He worked through and he found this. Tree with this property, and that you could delete 4 or delete 8, and the character polynomial was the same. And so that tells you get a pair of co-spectral trees. Now, in a certain sense, the really remarkable part of what Schwenk did was he then proved that if you look for the portion of trees which contain something like this. This rooted at 4. Okay. Now, if I see a tree and I can see this stuff attached to a vertex like that, it is at that vertex 4, then I can in some sense move it over and replace it by a copy of this stuff. So there's the surgery operation. If your tree contains this limb, I'll do that. If a tree contains this limb, then I can replace it by that limb, and it's still co-spectral. What Schwenk proved is that the proportion of trees on n vertices which contain a given limb doesn't depend on the structure of the limb. It only depends on the number of vertices. And using that, he was able to prove that the proportion of trees that don't contain that limb goes to 0 as n goes to infinity. And so he deduces that almost all trees have a co-matching mate. Now, it's not quite clear where this really kicks in. If you look at the actual trees and do your calculations, see which one's co-spectral, you get quite a lot of co-spectral trees on small sizes, but it's not clear that whether Schwenk's proof cuts in until you get to 50 vertices or 100 vertices. So there could be lots of things causing co-spectrality that don't come from this operation, but this is enough. Now you can do more with this. I'm going to construct another tree on 11 vertices. This construction is due to a couple of chemists. I mean, the chemists did a lot of the early spectral stuff. So I'm starting with a 9 cycle, and I've added 3 more vertices, 10, 11, and 12. So there's a rotation through 2, pi, and 3. And I'm going to focus on the vertices 1, 4, and 7. Actually, I'm not going to focus on 1, I'm going to throw it away. If I do that, I get a tree on 11 vertices. And the cute thing, if you look at vertices 4 and 7, I don't know why I wrote extra 1 there, but if you look at the vertices 4 and 7, then tree drop 4 and tree drop 7 are actually isomorphic. So they're co-spectral, and their complements are co-spectral. And Schwenk's argument tells you that almost all trees have this guy as this guy rooted at 4 as a limb. And so it follows from that not only does all trees not determined by the character polynomial, they're not determined by both the character polynomial and the character polynomial of the complement. And Brendan McKay later on produced a tree on 16 vertices, which also guaranteed that the Laplacian and the character polynomial distance matrix and every polynomial you're likely to think of fails to determine a tree. Okay, so that's the situation for character polynomial. So the point is, so trees are not determined by the character polynomial, so they're not determined by the matching polynomial. So that makes the question about which, when a graph's determined by them, or what proportion of graphs are determined by their matching polynomial. Now, in some sense, you can go pretty crazy with constructing co-matching graphs. This diagram's a little bit of a mess, but the idea is there's an 8 cycle there, and I've got 2 different extensions. I can add a vertex with the 3 red edges, or a vertex on another vertex attaching with the 3 blue edges. So I get 2 different graphs on 9 vertices. Now, what I claim when you do the vertex recurrence, well, you're going to get T times the matching polynomial of the cycle minus the sum of the graphs you get when you delete the neighbors of your chosen vertex. Now, the point about the H cycle is that no matter which vertex you delete, they've all got the same matching polynomial. So the sum in your vertex recurrence is going to be the same. And so the graph, my H cycle with the blue edges is co-matching to the H cycle with the red edges, and they're patently not isomorphic. Now, I mean, you know, you could do, you get some graph on 32 vertices with the order of order 32, which is trivially small, and then I can start picking sets of size 16. I'm going to get vast families, a vast family of co-matching graphs. Okay, by this one vertex extension trick. And so the other thing, okay, so I've been talking about complements on and off. The other thing is that Colan noticed that 8 vertices, if you go through and sort the graphs into co-matching families, there's a unique family of size 38. Now, since the matching polynomial of the graph determines the matching polynomial of the complement, if you have a cospectral family, the complements are a cospectral family. But since there's only one set of size 38, this set of size 38 must be closed on the complements. So the biggest family of cospectral graphs has got the property that on 8 vertices, there are 32 of them, it's got the property that for each graph, each complement is in there. Now, I haven't gone through and checked. Some of those graphs could be self-complementary, but they're not all going to be self-complementary. There's not enough. And on 9 vertices, there's a unique set of size 188. Okay. And so this leads me to the question I've sort of been hinting at. Are almost all graphs determined by their matching polynomial? Now, as of this morning, I'm inclined to think probably not, but I'm not at all confident, and my view has tended to change. So there's two things you can do. Actually, you can look at the data, and I'll say a bit more about this after this. I want to talk about an approach which we thought might work. So we had this idea of, you know, so I'm talking about an extension of a graph by taking one more vertex and joining it to a subset S in the original graph X. So I'm thinking that as the cone over the set S. Okay, and if the sum of the matching polynomials of the graphs X drop A for A and S is equal to the sum for X drop A for A and T, then the two extensions are co-matching. So we have this concept of co-matching extensions. Now, there's a rather nice way of setting this up. What I'm going to do is I'm going to write down the matching polynomial for each of the vertex of the subgraphs, in this case, of the path on 4 vertices. So if you delete the first vertex from a path on 4 vertices, you've got a path on 3 vertices, that's got matching polynomial t cubed minus 2t. If you delete the second vertex, you get an isolated vertex, matching polynomial t, and an edge, matching polynomial t squared minus 1. And so I've written down, not very difficult, the 4 matching polynomials of the vertex lead subgraphs. And then, because I like linear algebra, I'm going to write those polynomials and convert them to rows to vectors, row vectors, and I get a number of vertices by something for a half number of vertices matrix. Now, I haven't bothered putting in the 0 columns for obvious reasons. I don't need them. Now, the point is that these two extensions there, which are the two graphs I started with, I think a lot of mileage out of those. These two extensions in the for the blue case, I'm adding 1 and 2. So that's t cubed minus 2t and t squared minus t. And for the red one, I'm adding t cubed minus 2t and t cubed minus t, the same thing. So those two things are co-matching. Now, actually, let's leave that question for a bit. I'll come back to that. It's not going to fit in now. So let's be a bit more brag about this. So in other words, I can think of my subsets S and T as being given by the characteristic vectors, say alpha and beta. And they're going to be co-matching if alpha transpose that matrix C is equal to beta transpose that matrix C. Now, you might say, well, they could be isomorphic. Well, yeah, they could be. The general principle in these things is when you're trying to prove something that's some construction of co-matching things or co-spectral things, proving they're co-spectral or co-matching is generally the easy part. It's proving that they're not isomorphic tends to give you the headache. But it's not particularly different in this case. And besides, most graphs don't have any symmetry anyway, so we don't have to worry too much. So I'm just going to ignore that. So the point is, okay, if alpha transpose C is equal to beta transpose C, then the two extensions are co-matching. Now, or put another way, if the transpose of alpha minus beta applied to C is 0, so if alpha minus beta lies in the kernel of C transpose, then you'll get a co-matching extension. Now the point is, now we have kind of a machine, so we can write down this matrix of polynomials, I call it the characteristic matrix of the polynomials, and look for 0, 1, -1 vectors in the kernel of the transpose of that matrix. And basically, each time you find such a vector, you've got yourself a pair of co-matching graphs. And this works quite well for the graphs through 9 vertices. Okay, and you start to think, oh, I might have a way of proving that almost all graphs are co-matching. Now, the problem with that is, well, Caroline did computations just on random graphs on sort of 9 through 15 vertices. So take a random graph and try and see how many extensions you can find. And what seems to be happening as the number of vertices gets larger, we're getting fewer and fewer extensions, co-matching extensions. Okay, so that's why. So if you, with thinking that co-matching extensions would give you what we needed, well, that's probably not true. Although these sort of calculations should be done twice. Something a little similar happens with characteristic polynomial, because if you look at the plot for the graphs on n vertices versus the number determined by the characteristic polynomial, well, up through 10 vertices, it basically seems to be increasing. And there's a parity effect, but it basically you're getting fewer and fewer. It seems that you're getting fewer graphs proportionally determined by the characteristic polynomial. Okay, it's not till then Bauer and Spence did 11 and 12 when you could start to see numbers dropping a bit. But the other thing that happens is that we do have a construction which I call local switching, which is quite effective for producing co-spectral graphs. And if you subtract the examples produced by local switching, then the data seems reasonably convincing that the proportion of graphs determined by the characteristic polynomial will be going to 0. And now you can show that local switching asymptotically is not going to do any damage, it's too restrictive. So that's why Harmer has conjectured that almost all graphs are determined by their characteristic polynomial. Okay, despite the fact that if you just have a quick glance at the data, you might think that's wrong, but there's good reasons for believing it. Now for the matching polynomial, as I said, I'm not. I was fiddling around. There are two things here. So I ran through the graphs on 4 through 9 vertices, and this column here is giving the number of co-matching families of size at least 2. So it's not a number of graphs; it's a number of families. Okay, but so this was just me doing a quick and dirty calculation, and so you can run through all this. I mean, this is you. I mean, you don't even have time to go for coffee, really. So it's straightforward. And so you get those numbers, and if you go from 1044 to, or from 7 to 8, number of the graphs grows by 12, and the number of families grows by something like 8. Whereas the next one you go by something like 20, and the number of graphs is increasing by 20, but the number of families is only increasing by 10 times the previous number. So you can look at that, you may feel, well, maybe the proportion of graphs determined by their matching polynomial does go to 0. I don't have a strong feeling. The last column there is the number of graphs with integer matching polynomials. And so just for the fun of it, I did that too. Well, I was provoked a bit because there's actually a paper where somebody worked out the graphs on 8 vertices with integer matching, only integer matching zeros, 10-page paper. And they would have had access to Sage, so I don't quite understand what they were trying to do. But so there's exactly 2 graphs on 8 vertices, integer zeros, integer matching zeros. The other thing here is a link. It's a long URL. If the first part is just gets you to my web page, so you want the HTML_notes mpol-refs.html, that gives the some references to this talk. And So thanks to your attention. And since Crystal is here, I won't make any jokes, but thank you.
Thanks. Great. Wonderful. All right. Do we have questions for Chris?
¿No sabías?
No, no sabía.
Is that a question?
I can't hear anyone.
No? So those graphs you searched for at the end there with the ones with the integral matching polynomials, is there anything remarkable about the graphs themselves? Like, are they structurally resembling each other in any way? Is that too much to hope for?
The problem, well, this is an explanation, not an excuse. I started working on this, this was, we did have computers. It wasn't that long ago. We didn't have much computational power. In fact, the way I got started on this subject was I was traveling to a conference with Gutmann, and Gutmann defined the matching polynomial with a graph. I thought about the Coast polynomial. And then he said he believed that the zeros in matching polynomial were always real. Now, we didn't know at the time that it had been proved by Hahn and Lee, but that's beside the point. So, well, actually, I didn't believe him. I couldn't see why it would be true. I mean, there is a relation between the two polynomials, but it's not at all obvious. You take the Coast polynomial, do some brutal operation, and you've still got real zeros. So then he said he'd done some computations. And so, well, I thought, at that time, some mathematicians had done some computations. They might have looked at a dozen examples. And so I said, again, I still don't believe it. How many computations did you do? And then he said he'd done several hundred. Okay. And using a computer, but it would have taken a long while. And so then at that point, I decided I did believe him. And but so the issue is that we could work with Coach polynomial fairly well. I mean, Brendan and I did a fair bit of work with computations on Coach polynomials. The matching polynomial is harder to compute. If you just use recurrences, it's exponential. You can use the complementing to speed it up, and so the current programming stage runs quite quickly. But then, so I worked on the matching polynomial, and then I went on to other things. But because these days we have lots of computational power, and so there's lots of computational things we can generate, which would be interesting. And so, for example, what's going on with these graphs, I don't know. Okay. There's also, you've got a family of 188 Comatching graphs on 9 vertices and 32 on 8 vertices. We have no one's really looked closely at those. Caitlin looked a bit, but nothing. I never heard anything about it. So almost any interesting computational question, it hasn't been attacked computationally, and so there's a fair bit of low-hanging fruit. The same thing, the consequences of the Edmonds-Golay theorem. No one's looked closely at that.
Other questions?
Yeah, I have a question, Chris. Is there a graph that is not vertex transitive such that every pair of vertices is pseudo-similar?
Well, I actually had a question which I went past. I don't know if there's an example of it, or pseudo-similar. So I don't know if there's an example of a graph where that characteristic matrix has got rank 1, where the vertex deleted subgraphs all have the same matching polynomial.
Yeah, I know, I didn't find one. That's why I'm asking you.
If all vertices are pseudo-similar, you might be able to prove the thing is transitive. That seems a bit strong. Pseudo-similar means that the x drop A and x drop V are isomorphic. X drop A and x drop V are isomorphic, but no automorphism takes A to B. I would have thought that if all vertices were pseudo-similar, the graph was vertex transitive. But I certainly have no example of that, because I don't know a construct a graph with all vertices pseudo-similar that's not vertex transitive. But I can't construct a graph where all the vertex leading matching polynomials are the same, and I strongly suspect that such a graph does exist. Not
Do you
sure what
think the
reason
graph
is.
does exist? A non-vertex transitive graph such that every pair of vertices is co-matching?
I think there's a reasonable chance. I mean, if I had to bet, that's the direction I would go.
Okay.
I mean, I have no evidence, so I can't make it. You know, I've got no grounds making a conjecture because I have no evidence either way.
Would such a graph have to be walk regular?
Not. In
It has to
general,
be
no,
regular, right?
Yes. You can tell the valency, so you can tell if the matching polymer, you can't tell if the graph's connected. You can't tell whether it's bipartite. You can tell if it's regular, I think. Well, yeah, because in that context, you've got the number of edges. If you know the matching polymer of the graph and the matching polymer of each vertex subgraph, then you know the valency of each vertex. Yeah. So. Now it's not clear whether you can tell whether the graph is regular. That's embarrassing.